Good morning, everyone. Thank you, Dr. Dimbate and Dr. Moore, for hosting this seminar. My name is Sagar Panthi. I'm a graduate research assistant in pollution prevention team here at WVU. And today I will be presenting on a carbon-aware distribution framework for perishable supply chain, focusing on West Virginia milk case study. This work explores how we can make the delivery of perishable good more efficient and environmentally friendly. The result of this case study is adopted from the previous work of another researcher in the pollution prevention team. Here is the roadmap of our discussion today. We'll start by looking at the broader picture of greenhouse emission within the supply chain, then dive into what constitute a green supply chain. The core of the work involves an integrated optimization framework which tackles the complex milk collection problem. We'll break down the two optimization technique used in the research, namely the set covering problem and the vehicle routing problem. Finally, we will walk through our case study in West Virginia, share the results, and conclude with key insights and future directions. Let's begin by understanding the environmental impact of supply chain. So transportation or hauling, for instance, contributes approximately 8% of global CO2 emission. When we talk about perishable good like milk, the challenge is even greater. The transport of chilled food is particularly energy intensive, with refrigeration alone burning up to 40% of the fuel. Looking at the broader picture of the livestock supply chain, it accounts for a significant 14.5% of all human-induced greenhouse gas emission, and the processing and transport of all animal products contributes about 6% of that figure. We can see the picture on the right. The picture shows the total emission of transportation in year 2015, which is almost 4 billions of tons of CO2. This number is only projected to go up. So, how do we address these environmental concerns while still meeting the demand? So, we know that perishable goods, by their nature, have a limited shelf life and they require timely delivery. When we talk about milk as a product, this means optimizing its collection from various farm to processing plant, ensuring its freshness, and minimizing waste. This is what we refer to as milk collection problem. Our solution lies in integrating cost minimization with emission reduction strategies to achieve what we call sustainable operation. We achieve this we achieve this through an integrated optimization framework. So our goal in this framework is to minimize overall cost, reduce environmental impact, and, and lower emission, and most importantly, maintain milk quality. So here is the integrated framework designed to solve milk collection problem. It combines two powerful optimization, mathematical optimization technique. The first one is set covering problem or SCP. The SCP help us to strategically decide where to locate our collection depot and which farms to assign to the depot. So I'll discuss about SCP in the upcoming slides in detail. And the second mathematical model is vehicle routing problem, or BRP. It helps us to optimize the route for our collection. It optimizes the vehicle route from those depot to the farm and the back. By modeling both these together, we create a comprehensive solution. Both of these problems can be solved using technique like mixed integer linear programming. So again, the goal is to minimize cost and reduce environmental impact. But when we look at the broader picture of milk collection and agricultural logistic, there are several unique challenges. The first challenge in the agricultural logistic is obviously the challenge of perishability. If the product are not collected or delivered within the strict time window, they degrade in quality and may even become unusable. Um, the farms from which the milk is collected might be located in the rural area with no good road network, which makes the routing challenging. Similarly, we are trying to minimize our cost as well as the energy used, but both of those energy and the cost might depend on multiple parameters, and optimizing them might be difficult. So these are the challenges, and also always there are consideration like environmental impact, regulatory compliance, and the yield from the farm is unpredictable. So the milk farm may not produce same amount of milk every day. So that is also a challenge regarding this. So, to solve these challenges in agricultural logistics, there has been a lot of previous work. So, here I will discuss some of the previous work and some of the methodologies the previous researcher used. So, most importantly, they divide the work into three uh, group. One is the defining the objective function, then doing the emission modeling, and also defining the carbon boundaries. So for objective function, some researcher combined CO2 emission and energy into a single cost function. So what they did is they combined all the cost related to energy emission and fuel consumption into one, and they try to minimize that cost. So likewise, in terms of refrigeration, if the vehicle has refrigeration system, then some researcher directly incorporated the refrigeration cost into a single variable, while other researchers separated CO2 as a refrigeration as a different component as well as CO2 as a different component. And for emission modeling, there are two primary sources of emission. The first source of emission is the fuel consumption due to transportation. And in some cases, where we use refrigeration system in the vehicle, there is also a emission, greenhouse emission from the refrigeration itself. So in emission modeling, those both can be taken together. Or in some cases, if there is no refrigeration, instead of refrigeration, some vehicle may have really good insulation. In those cases, we can ignore refrigeration, and there has been researcher who has done this. And also considering our scope of carbon boundaries, um, depending upon our scope, we can take tank to wheel, which means the carbon boundary, which refers to the emission from the vehicle's fuel consumption only. Or we can expand our scope and use well to tank, which covers emission from fuel production and delivery. So depending upon our scope, we can use tank to wheel or combine tank to wheel and well to tank into well to well. So these were the work of the previous researcher, and their assumption, their uh, scope. So in our methodology, this is the methodology that we applied in our work. So the first step is a literature review, which I discussed in previous slide. The second step is data collection. In in the study, the data was collected from 33 farms from West Virginia. The data consists the collected data consisted of farm location in form of longitude and latitude. Using Google Maps API, the location was converted into distance and time metrics, which consisted of distance and time between each farm as per the Google Maps. After implementing the set covering problem, the vehicle routing problem was implemented. To solve set covering problem and vehicle routing problem, solution to tools like mixed integer linear programming and meta-heuristic were used. I will discuss both SCP and VRP detail in upcoming slides. So before going into set covering problem, vehicle routing problem, and their modeling, uh, let's discuss some of the assumptions. As I mentioned previously, there are many real-world challenges in agricultural logistics. These challenges needs to be addressed through simplification or assumption. The main challenge, for example, perishability and quality decay, can be dealt by imposing hard time constant, uh, hard time and as well as temperature window, meaning that milk must be collected within a specific time frame to prevent spoilage. Also, regarding fuel use, which can be highly dependent on factors like load, terrain, vehicle speed, model can be simplified by making the fuel consumption dependent primarily on the distance rather than complex energy function per arc. So we'll continue with the modeling assumption, addressing the challenges. So another challenge is the heterogeneous farm yield. So each farm may not produce same amount of milk each day. So for this, we assumed that the production of milk from farm is deterministic. So we know in advance how much milk is being produced from each farm. Also for rural road network, we pre-screened to exclude infeasible road and used only those paths provided by Google Map. Uh, and we use shortest legal path in that case. And also, mm, when we are establishing or when you are trying to open a new depot, there should be some limitation on the size of the depot, that its resources and its capacity. So we set up some upper limit for depot capital. Finally, the driver hours need to be limited, ensuring route times are less than predefined hour of service. So these were the challenges regarding fuel consumption and energy uses. So we are also trying to minimize the emission, and emission depends upon a lot of factors like vehicle characteristics, road condition, load and velocity, environmental factors, and like in the scope of our research, it was hard to cover all those factors. So we simplified that by assuming that the emission from the vehicle is dependent only on the distance covered by the vehicle. So that was the assumption regarding emission. Now let's go into the mathematical model. As I mentioned earlier, we are using two mathematical model. One is set covering problem and the second is vehicle routing problem. So the first crucial part of our optimization framework is addressing where to collect milk. So this is solved by the set covering problem. Um, So in terms of strategy, this is the strategic phase where we want to open our depot or hub. The key constant is that each farm needs to be close enough to one of the depot. So we are trying to open a new depot and it obviously our depot needs to be nearby the farm, or the farm, all the farms need to be nearby the depot. So but we also know that opening a new depot costs money, a significant amount of infrastructure, and as well as operation cost. So, a core objective is to open as few depot as possible while still meeting our coverage requirement. So, our ultimate goal is to set our ultimate goal with the set covering problem is to cover all dairy farms, ensuring every farm can deliver its milk to assigned depot within the time limit, all while doing so with a minimum number of depot. We start with the dairy farm location. We then identify potential of candidates among them. We evaluate that coverage to see which farm they can reach, and through this process, we work to minimize the total number of hubs, ultimately leading to an efficient hub network. This ensures comprehensive coverage with optimal resource location. So here is an example of how set covering problem work. Suppose we have a large number of farms and the set covering problem will select one farm as a depot or as a hub, and then it will try to assign all the farms to it. But it turns out only the farm number, for example, in this case, only the farm number 7, 8, 9, and 10 can be reached within the distance, like within the time of 1 hours or so. We call that maximal coverage distance. And we cannot reach other farms within that time frame. So what it does, it tries to establish another depot and try to assign all remaining farms to it. And if all the farm are reachable from that depot within the time frame of 1.5 hours or the time frame that we set, then it will assign all the farms to it. If those farms are not reachable, then it will open new depot and assign remaining farms to it. So basically, what it is doing is making the cluster of farms depending upon how far they are with each other. So now we have used the set covering problem to identify optimal location for our milk collection hub. The next critical step is to figure out how to actually uh, get milk from all individual farm. So this is where bagel routing problems comes into play. So for example, in this case, we have selected two cluster or two sets. Now we want to decide where to go from, for example, D2, from depot 2. We can go to farm 1 first, or we can go to farm 4 first, or farm 5 first. So the sequence where to go first and then second and third is decided by bagel routing problem. So what it does is uh, it designs the best possible route for our milk trucks, keeping several objectives in mind. So the first objective is we need to visit all the farms. So this ensures that truck is visiting all the farm. The second is we want to minimize the cost and we want to minimize the emission. And both the cost and emission and even the fuel is dependent upon the distance traveled. So it tries to minimize that distance. And also we want to make sure that the truck are not full. We Each truck has certain capacity, and it also takes that into a consideration. So as shown in the figure, we start with the scattered farm location. Through route planning and distance minimization, we work towards greater fuel efficiency while also managing capacity, ultimately leading to highly optimized and sustainable truck routes. So let's go into the case study. As already mentioned, the first step in the methodology was data collection, which was collected by the previous researcher from the Department of Agricultural here at WVU. The data consisted of 33 farms. The data consisted of longitude and latitude, as well as the production per day. Here in the figure shows the farm in the black dots plotted in the West Virginia map using the OpenStreetMaps API. Also, the distance in the form of time taken was calculated using Google Maps API. The data, so first, after plotting this data into the map, the plotting was done just for the visualization. The actual problem solving does not need to plot the data. So after this step, the set covering problem was used. So here we can see the example of set covering problem. So like I already mentioned, what set covering problem does is it finds the cluster. But to make the cluster, first it select the depot and then it assigns farms to it. And the number of cluster is dependent upon the maximal coverage distance. So if we use the maximal coverage distance of 1.5 hours, it will select 5 depot. If we use the maximal coverage of distance of 3 hours, it will get 2 depot. That means that if we are using a longer travel window, then less number of depot is okay. So also, we want to have the depot opening cost. So for this work, it was fixed at 500,000. Now, let's take an example how vehicle routing problem works in this case. So following the depot selection, the vehicle routing problem then determine the most efficient route for each depot. For example, For depot 2, located at farm number 18, here in the figure, it is represented as a blue dot with the number 5 on it. We simulated a homogeneous fleet with two trucks, each truck at the maximum capacity of 3,000 gallon. This zoomed in map provides a closer look at a specific vehicle routing problem. The different color lines represent the optimized route for individual trucks from a farms to depot, illustrating how the model efficiently connect farms to ensure timely milk collection. This cluster was this was simulated only for the demonstration. In the actual case study, only two or three clusters were used, and vehicle routing was used for only those. And here in the cluster, you can see that mm, in this particular cluster, there are two vehicles used, and it has two route for the two trucks. So we can see that for blue, the path is from 5, 4, 3, and 2, and it can follow that route, which is the most efficient. And same goes for it has the similar pattern for red path. Now let's look at the impact of the optimization. We compare the optimized scenario against the baseline of two depot haul. The baseline setup involves 4,671 miles of travel, resulting in 6,592 tons of CO2 equivalent emission. The vehicle routing optimized scenario with one truck reduced the total miles to 1,555 and CO2 to 2,194, which is remarkable 66% reduction. Even with the two trucks, the multi-vehicle routing optimized scenario showed a 67% reduction, bringing emission down to 2,155 and over the distance of 1,527. These are the significant environmental saving. Um, it is to be noted that while this model uses only two depot and two vehicle for computational traceability, real-world operation might involve more. The simplified case studies allows for the controlled analysis of set covering problem and vehicle routing emission. Likewise, if we look from the economic perspective, our optimized solution also shows substantial benefit. The baseline two depot haul has a cost of 0.45 per gallon of milk and transportation cost of 6,521. The vehicle routing problem optimized with one truck scenario reduced the cost per gallon to 0.18 and the daily transportation cost to 2,554, leading to a daily saving of nearly 4,000 and break-even point for depot in less than a year at 0.94 years. Even with three depot multi-vehicle routing optimized with two truck scenario, we see significant saving and break even at the point of 1.5 hours. So it can be seen that there is no significant difference in the daily saving between two depot and three depot, but the break even point is quite different. It is because of the associated depot opening and operation cost throughout the years. So this was the economic perspective. Let's go into the conclusion. In conclusion, this research provides a robust carbon hour distribution framework, and although it has been used for milk collection problem, the research can be applied to other agricultural products, and this approach offers powerful tools for enhancing sustainability in perishable supply chain. So these are the reference I used for my presentation. Thank you for your time and attention. And here is a feedback form uh, that will be helpful for me in the future presentation. Thank you.